So tonight, you're going to hear from a coastal archaeologist, Dr. Laurel Breece, who got both her MA and Ph.D. from UCLA, and she's a professor at Long Beach City College. And so please join me in welcoming Laurel Breece to start.
And good evening. Okay, I'm always excited to talk about archaeology, but I am particularly interested in talking about archaeology and putting it into the context of global climate change and changing coastlines. It's not original with me, but if you don't know where you've been, then you don't know where you're going. So we're going to be taking a look at our changing coastlines from an archaeological perspective. So this will be kind of a hopscotch approach around the world, and we'll focus on 3 sites that are vastly different. A land bridge that enabled the peopling of the Americas, a cave art site in France, and a burial site in Florida. I do have to let you know that there is an image of human remains from the Florida site. And then we're going to take a look and talk about what we have learned archaeologically about our most vulnerable coastal areas, and we'll focus on a site in Lower Manhattan. Finally, we'll discuss the problems and prospects of maritime archaeology and studies of submerged sites as a way of adding to the discussion on changing coastlines. So let's get started on our archaeological journey around the world. Okay, so first of all, first up on our sites, we're going to look at the Bering Land Bridge. So Beringia is now, sorry, it's hard for me to see up there. Beringia is now underwater and spans about 55 miles between Alaska and Florida, excuse me, Alaska and Siberia. Okay, so this was once a land bridge that allowed the first humans to cross over from Siberia. And during the Ice Age, the sea level fell about 300 feet, and that landmass was about 1,000 miles wide. Okay, so looking at Beringia, we've got the current coastline, and then we have the ancient coastline. Sorry. So we know we came out of here somewhere about around 12,000, before 12,000 years ago. That's one of the biggest questions in archaeology, is when did we get to the New World? When did we come in here? And it's very difficult finding accurate sites for this. So we do know that they crossed over this land bridge, probably following the game. Okay, and then after they got here, we've got these different migration patterns. So we do have people who stayed up in the Alaska area, but we're also kind of interested in what happened and where they came after that. Okay, so we do still have Inupiat. They were some of the descendants of the original people who crossed over. Okay, but now we're going to follow that pathway down and find out what happened and what do we know about the peopling and what kind of time frame do we have. Okay, so in taking a look at Florida, we're going to look at some submerged sites here. So we have the current coastline here and the coastline before the end of the Ice Age. So the first site that we found here is over here in Venice, Florida. And this is a burial site that you might have heard about in the last couple of weeks. It was just found about 2 years ago, and National Geographic is going to be running a story on that. Okay, so here's the thing with the title here. So the archaeologists found human bones, sharpened wooden stakes, and textile fragments. That's going to be really a clue later on. One of the things I do want you to see, what is so difficult about doing underwater archaeology, is that it's really hard to see. And it's very, very difficult. So if you think about even finding these sites, so what happened, a diver was there, found what he didn't even know it was a bone, kept it on his kitchen table for a few weeks, and finally he looked at it and thought, this may be human. So he turned it over to Florida, and they decided to go out there and do the excavation. Okay, so what they're doing here is they're trying to tag all of the artifacts that they're finding. Okay, and again, you see the difficulty in these underwater environments, and we're going to keep talking about that, how hard it is to find these sites, and when you find them, how do you excavate them? Okay, so how did they even know that this was a burial ground, just with those few things that they found? So we're going to take a look at another site in Florida, here on the other side, and this is the site of Windover. Okay, Windover is a bog area. They were going to be putting in a housing development, and then the construction crew came across human bones. And when you find human remains, you have to call in archaeologists, and then they try to see what's going on. And the housing development company, they let them excavate the entire site before building their houses. Okay, so in this excavation area, it was in a bog area, and in the bog, they found these individuals there. There were about 161 individuals that they excavated. So this is a very common burial practice in southeastern Florida at this time. This burial site was in use from about 8,000 years ago up to 7,000 years ago. So what they would do, they would go out onto the bog, and they would put the individuals on like some kind of animal skin, and then put a covering at the top, and then use those sharpened wooden stakes to keep them buried. Okay, so think back to the Venice site. That's what we found. They found the same things: the human bones, the sharpened wooden stakes, and the textile fragments, and that's exactly what we see here. We did notice something in the bogs, though, that in some of the skulls, they saw that they seemed to be filled with something. And they thought at first that maybe it was just like some of the silt or the mud from the bogs. But it turns out that of those 168 individuals, 91 had intact brain tissue. So the interesting thing, though, is that when they did the DNA analysis, the DNA showed that they had more in common. They were related to Native Americans from South America, and not from North America. So we already know that they're heading south. Okay, so what the Ice Age has enabled us to is to people the New World. That's part of the best of times. Okay, we're going to move off to the other side of the world and take a look at the Cosquer Cave in the Mediterranean. So the Cosquer Cave. It's called the Cosquer Cave because it was found by Henri Cosquer, who was a scuba diving instructor. And he had taken one of his clients out, and as he was diving, he saw that there was an opening into a cave. So he went in a little bit, but then he came back out and decided that he'd come back another day. So one of the problems with this, he did come back, and he did go in there. This cave passage is 450 feet long, and it's only 2 feet wide. And so Cosquer said as he was going in there, like his fins are, all the silt is coming up. He couldn't see anything, and he couldn't turn around. So Cosquer has always said he just prayed that it would open up and that he'd be able to turn around and get out. When he emerged in the main chamber and he surfaced, the first thing he saw was this handprint here on the wall. And he said he couldn't believe it. He thought it was some kind of a joke. And he thought, who would do this? Who would come into this cave and draw on the walls? So he thought he really needed to tell someone about this. So he called the French authorities, and some of the people, this is Henri Cosquer here. There's an archaeologist, Jean Courtin, and Jean Clot, who is the world's leading expert in Upper Paleolithic cave art that spans from about 30,000 up to about 18,000 years ago. So the way they determined the authenticity, first of all, when you look at you've got the cave wall and then the images on the cave wall, but those images are now covered by calcification. So that indicated that they were original, they were authentic. Later, the site was radiocarbon dated to about 27,000 years ago for the first section of art. And then the later section was dated to about 18,000 years ago. So this is the same time period as the Great Art Cave of Lascaux. Okay, so some of the things that we see in here, some of the horses that we've seen like in Lascaux and other cave art sites, but this is the first one that's ever been found in the Mediterranean, in this area. And so one of the animals that was depicted right here, at first they thought it was a penguin, but now they believe that it's a great auk, which is a 3-foot tall sea animal, tall flightless seabird that was completely docile. Okay, so how did the cave end up underwater? Originally, the cave was about 250 feet above sea level, and 7 miles inland. And then as the glaciers melted, the cave became submerged. And fortunately for us, the art was completely protected by this cave environment. But that's not happening anymore. The cave is flooding. The Mediterranean is rising, and many of these chambers are completely flooded. So the French government, what they've done is they've come in, they have people who are mapping like every centimeter of the cave wall, and they're reproducing that cave site, which should be open in the next few years in Marseille. And there's our final view of the handprint. I do have to say the cave is now sealed. The French Navy sealed the cave because 3 divers lost their lives trying to get into the passage, because it's not a straight passage. There's many kind of areas that go off the main cave, so they've had to seal it off. Okay, so far what we've seen is what was made possible by the glaciation and the subsequent flooding. We looked at the peopling of the America, that intact preserved burial site, and it's preserved because it is underwater, and this cave art that has now been protected. So that's what we are now going to look at is what we've learned from an archaeological perspective about how we have created our own vulnerable coastlines. So the site we're going to take a look at is called the Ronson Shipwreck. This was in Lower Manhattan. Okay, when you look at Manhattan today, it's really hard to, I'm sure many of you have been to Manhattan, and you know it's very, very flat, but that's not conducive for building all of these structures. So it's really hard to believe that that Manhattan was once a jungle area with hills and valleys. If you go to Upper Manhattan, you go to Fort Tryon Park in the Cloisters, this is the original topography of New York. This is what it would have looked like. But that, you can't build on that. So what they did, all those hills and valleys, the hills were leveled and the valleys were filled in. Okay, one other thing here. So what you're looking at here, this is the original coastline of New York. This would have been in the 1600s, New Amsterdam. And what you're seeing here is the area that has been filled in, and we'll talk about why that happened. So this used to be in the early 1980s. There was the Blue-Green Line project in New York. That's the art installation. So the Blue-Green Line was painted all around Lower Manhattan to show you that was the original coastline, and that was the original, the original water line and the original coastline. So this, I got to see this Blue-Green Line. It was not meant to last. It did last for a number of years, but it went everywhere. It went like up over buildings, over fences, down streets, through gardens, everywhere. So you could actually follow this pathway and see what was the original outline of the island. Okay, so what happens in 1982? You're looking at, that's the South Street Seaport right here, which does look a little bit different today. So we're like 3 to 5 blocks in from the South Street Seaport. Oh, this stuff is called snow. All this really, really cold stuff. So what happened, there was an archaeology project on Water Street. They were going to take up this parking lot and build a 30-story office building. So before they did that, they brought in an archaeological team to make sure that they were not impacting any cultural resources. So we knew that there was a merchant area there dating to the 1800s. That's in all the documents, and it's on all the maps. So that's what we were brought in to do, and we were brought in to do this in February. So, yeah, it was a little chilly. Pardon? Okay, so we started to do this. Now, when you do archaeology, and even though you have maps, you don't know if those maps incorporate everything, that there could be things left off the map. So what we put in, we call these a series of deep tests that we put around the site. And these deep tests went down between 30 and 40 feet. In one of the deep tests, it looked like we came onto the bow and the beak of a ship. And this was the last day of the excavation for the merchant area. That always happens. You find everything on the last day. So they brought in a team of archaeologists from Texas A&M, from the Institute of Nautical Archaeology, They got there, one of them went down in the hole, looked around, came up and goes, yeah, you have a ship. There's a ship there. So Mr. Ronson, who owned the property, graciously gave the team another month to finish the project, to see why this was there. You know, this is a slide that's taken at night. We were working 24 hours a day. We worked around the clock. There's a team of about 45 or 50 of us because we just had to get as much work done as possible. And again, just remember, we're like 5 blocks away from the South Street Seaport. So here's the ship. This is part of the ship here. I always think if OSHA were here, they would really be concerned about some of that, shoring there. So, like, why was the ship here? Like, why is there a ship 5 blocks in? And it goes back to the 1730s, when shipping was one of the most important financial activities in New York. New York needed 2 things. They needed a deep water port, and they still needed more land. And they'd already, altered the landscape, but they needed more land. So in the early 1730s, if you bought land, you actually didn't buy land in this part of New York, of Manhattan, you bought water lots. And then you had to agree to extend the island so many feet. So this was a concerted effort around the whole tip of Manhattan. So what happened, people would bring in these ships. So this was a merchant ship, and they would burn it to water level and then fill it with landfill. So this is the bulkhead that's holding up the landfill, and these ships ringed this whole area. One thing about this ship, we don't know a lot about shipping from this time period. We don't know a lot about the ships themselves, partly because the ships that didn't sink, they're gone. So we've always said we tell the story of the ships that didn't make that made it with the ships that didn't make it. Now this one was deliberately buried here, but we did it, and because it's not underwater, we had a really good chance to look at the construction of the ship. What you're seeing here are all the tree nails or the trunnels that are part of holding the ribs together. Okay, so we had a really good chance to document this and look at the ship hull construction. Okay, there's the entire part of the excavation. We could not excavate the entire ship because, just think about this, it's what's holding that landfill together. So that ship is still down there. We were able to excavate the bow and the beak, and that was it. We also, while we were doing this project, we shifted the street about 1/4 of an inch, and if we had removed any more, that probably wouldn't have been a very good thing. So the bow and the beak have been removed. It took about 10 years to finish the conservation. It's now on display at the Maritime Museum in Newport News, Virginia. Okay, so this is 175 Water Street today. That building is right on top of the ship. So just think about that. When you're standing there, you're standing on landfill. Okay, so that's interesting, but what does that have to do with creating these vulnerable coastlines? Okay, that's the original coastline of New Amsterdam. This is all that area that was filled in with landfill. And that's what happened with Hurricane Sandy. So we're creating our own vulnerable coastlines. Okay, so this is what we've learned from archaeology, but we really need to add more to the story. We are capable of doing that. So the new wave of archaeology, of maritime archaeology, is up to now we've always been focused on shipwrecks because, let's face it, they're exciting. They're really interesting, and they're easier to find. They've left clues behind. We have documentary evidence. We can go on that, the trail of those ships and find them. And then when we find them, we can actually see them. Submerged landscapes are much, much harder to find. So what we're doing now is we're going to look at how we're going to use blue technology to find these sites. Because think about what a prehistoric site would be. You're going to have stone tools. You might have like a rock ring that's used as a hearth with bits of burnt bone or charcoal. That's really hard to find, especially when you think about, like, you've got the site here on land, and then it's submerged now, which meant at some point it was in the intertidal level zone in a very high energy environment. So what's going to be left? How are we going to find that? That's what's been really difficult. So it's going to be hard to find these unless we use they're in protected areas. Okay, so here where we step in, this is like the new wave of what we're doing here in California. At Long Beach City College, we have this underwater robotics class where we're building these remotely operated vehicles. Because we don't want to just jump in the ocean and start swimming around looking for sites. We're going to have something do it for us. Oops. Okay, so the students are learning, they build these ROVs, everything. These are my archaeology students, by the way. They're not, electronic students. They're actually archaeology students. And they're putting everything together. They're doing the frame, they're doing all the electrical work, they're building all the circuit boards. So this is going to be one of our means of doing this exploration, looking for these sites. So LBCC has a very long and very close relationship with the Aquarium of the Pacific, and we frequently deploy the ROVs that the students build into the tanks at the aquarium. So here are some of my archaeology students getting ready to put the ROV into the tropical tank. Okay, here we are. Okay, so when we put the ROV into the tank, a lot of it is to show the guests here at the aquarium what we're doing and how we're going to start, exploring the ocean, because that's a really big topic with me too, is exploration. This is something you've never seen before. This is the world's first underwater selfie bot. So our students came up with the idea, they built it, they designed it, and then they built it. So what happens, the ROV gets close to where the guests are, and they're looking at it, and they can see themselves in a fisheye lens. So it would be like, okay, just to paraphrase Jacques Cousteau, it's as if the little fishies are waving hello at you. So here we are with the divers in the tank. So that's our job here, is to explain what we're doing. Okay, but we're going to need more than just an ROV. We're going to need other kinds of equipment. If we're going to look for these sites that are submerged, we're going to need something that's going to help us do that. So our first piece of equipment is a side scan sonar. And this is going to, when you look at an image from a side scan sonar, it takes the water away, and you're just looking at either the ocean floor, the riverbed, or the lake bed. All of our equipment was bought from J.W. Fisher's in Massachusetts. So we were back there learning how to use all the equipment. Here we're deploying it in the Fall River. Okay. And this is the kind of image that you're going to get from a side scan sonar. So what you're seeing here, so side scan does just what it sounds like. It goes down, it's called a tow fish. We tow it along behind the boat, and it scans to the side. And what it's looking for is anything that's protruding above the seafloor, or in this case, the river bottom. This middle column, that's the water column. So if you were to fold that up and not see the middle column, what you would see is what it's seeing on the right-hand side and what it's seeing on the left-hand side. So right now, this is a debris field that we found near the bridge area. We also can change the color scheme so things can stand out a little bit more. Over here, what it detected were the rib bones from a 21-foot wooden boat. So it's detecting things, anything. It can be organic, wooden, doesn't have to be metal. And then we're tracking it and mapping it as we go along, so we can build up these kind of mosaic maps of what we're finding underwater. Okay, so that's one instrument. But many of these sites, these prehistoric sites, they're not going to be above the seafloor. They're going to be below the seafloor. So we need to find some way of looking at that. So what we have here is our sub-bottom profiler. So the sub-bottom profiler, we're testing it here in the water. Oh, this is my favorite instrument because it looks like the Starship Enterprise. I just really like it. So the sub-bottom profiler, we can do it in shallow water just by holding it on a pole, or we can mount it on a boat and deploy it that way. And this is the image that you get with the sub-bottom profiler right here. For archaeology students, it looks like if you're digging in a terrestrial site, it's the stratigraphy or the layering of the earth. And this is what you're seeing below the seafloor. That's what it will look like. So if you're going to find, looking for a prehistoric site, nothing will be on the surface. It's just not going to happen unless it's a really protected area. But we will see it this way. It will have left clues in the stratigraphy, and that's what the sub-bottom profiler is going to do. Okay, so we have one more piece of equipment, and this is our proton magnetometer. This is like an underwater metal detector. And I do have to point out the young woman right here, Nicole Smith. Nikki is a volunteer here at the aquarium. She's sitting right over there. And Nikki is one of my archaeology students and part of the core group here. Okay, so the proton magnetometer, when we drag that one around, what it's looking for is anything metal. Well, that's not going to be a prehistoric site, but it will be any kind of submerged port sites. That's how we're going to find that. So we're dragging it along, and then it's going to just do a ping every time it encounters something metal. All of these instruments, the controls on the boat are GPS enabled. They'll have global positioning systems. So every time we get a ping, we know exactly where we are. Okay, so once we've done this, once we've finished like using all these pieces of equipment, we want to actually, well, in archaeology, terrestrial archaeology, we call it boots on the ground. You want to go see what's really there. Here, I call it fins in the water. You got to get in the water if it's diveable and see what we've got here. So communication is really difficult. We now have 4 of these full face masks that are communication system enabled. So the 4 are for the professors, the instructors. So we can talk to each other, we can talk to the boat, well, to the people on the boat. Now the students, we have 4 mother-in-law units. So a mother-in-law unit, they can hear, but they can't talk. Okay, so when we've narrowed our search down and we've used the proton magnetometer that we have deployed, then we want to get a little bit closer to that one. And so this is our handheld proton magnetometer. It's so precise, it can distinguish a single nail. So that's going to give us our real close-up look. What's really good about this is that it's high sensitivity to metal objects, but it's not affected by anything like highly mineralized saltwater, coral, or rocks with an iron content. Anything environmental, it dismisses that noise, and it just focuses on what we're looking for. We also have our handheld camera. So this is where we're taking our high-definition photographs, and we're doing our video recording at the same time. So we're documenting everything that we're doing. Okay, so this is my core group of students. They're the ones that are going to be doing this. So we've just started this program, and it's not unique to Long Beach City College that we're focused on these submerged sites. What we're really looking for now is the future of maritime archaeology. Like, what do we do? We've shifted our focus away from shipwrecks, and we thought that for archaeologists, the future lies in the past, and we have to be able to contribute to this conversation and add something to it. So in order to do that, we in California, I am part of the California Maritime Archaeology Committee, and we've now decided to shift away from shipwrecks and concentrate solely on submerged landscapes. That's our goal. So our committee right now is writing the guidelines and the standards for surveying, and that's what we're going to do. Is we're going to start mapping this, and hopefully give us another year or two, come back again, and I can show you some of the things that we found. So thank you very much.
And Gary Griggs, Distinguished Professor of Earth and Planetary Sciences at UC Santa Cruz, is going to speak. And Gary is the geology, I guess the laureate for the state of California. He's got 10 books, I think, now. Another one on the way, many papers, distinguished guy. We have 2 wonderful scientists here with us tonight.
Jerry gave a great introduction, and I would sort of put it in a few different words, saying we probably all agree that the shoreline is one of the most important lines on the planet. The shoreline is moving, and it's moving towards us. And it's moving towards us because sea level is rising. Sea level is rising because the planet's getting warmer, and ice is melting. And all ice melts at 32 degrees Fahrenheit. Doesn't matter if you're a Democrat or Republican. Didn't mean to offend anybody. or everybody evenly. So this is going to be quite different than Laurel. And I think when Jerry asks us to talk, he never knows really what he's going to get. But I think the topic of coastal change, and I'll just start by saying the climate is changing. That's not a debate. And this is just a plot of taking 1900 to about 1980, which is the black line, the average. And then these are the deviations or the anomalies from that. So if we go back and look at the late 1800s up to the 1920s, it was cooler than that average. And you can see it's getting progressively warmer. And I'm sure you've all been reading that, 16 of the last 17 warmest years since we started measuring. I don't know, something magical happened in 1880. We developed the thermometer or something. We started measuring global temperatures. Everything goes back to 1880. But all the warmest years have happened since 2000, with the exception of 1998, which was an El Niño's year. Well, this will tell you how long I've been in Santa Cruz. So 53 years ago, I had started graduate school at Oregon State University in oceanography, and we were working on the North Pacific, which I looked out at the calm waters out here today, and I said, this would be a great place to do archaeological research. The water was never calm 200 miles off Oregon. Well, we looked different then, right? I actually left surfing at UC Santa Barbara and went to do graduate work. Sometimes I wonder if I should have stayed, but I didn't. And what we were doing was actually piston coring. So we're using a 2,000-pound weight, a pipe in 20-foot lengths, 20 or 40 feet. This is not drilling, but we're actually dropping a weighted pipe. Bringing back, and it works something like this. Basically, the pipe has a trip weight, and when it hits first, it lets this fall under gravity, and then you, with any luck, you bring back 10 or 20 or 30 or 40 feet of sediment. And the ocean is this wonderful sink, and it records what's happening in the overlying water column. So as temperature changes, different organisms live and die, and we know, for example, during El Niño years, as the water gets warmer, we get Humboldt squid. And so as the climate changes, the types of organisms that live in the surface water change. And what we discovered, this was 200 miles off Oregon, but similar, and we're in 13,000 feet of water, was that in the warmer surface sediments, we found radiolaria were the dominant fossil that was preserved. These are microscopic. And as we got back into cooler temperatures, as the sediment got deeper, they were dominated by something called the planktonic foraminiferous. So we could actually do a paleotemperature analysis by looking deeper in the cores. And we could see warm, cool, interglacial, glacier. So this is my sort of first introduction to climate change 53 years ago. Today, around the world, we've got climate change recorded in a whole bunch of different places. So we've now drilled into the deep sea floor for 50 years around the planet, something called the Ocean Drilling Program. It's had several names. That's gone back 65 million years. And similar to the sediment cores we were collecting, this is now drilling. And we see climate change ever since we've had an Earth and a sun. We've had the climate change. So climate change is nothing new. We are now drilling into the ice of Antarctica and Greenland, and ice records temperature changes as well as things like volcanic eruptions. So when snow collects or falls, it actually traps little air molecules in there, and those air molecules have a memory of the temperature. It also includes other gases like carbon dioxide, and we can tell how much carbon dioxide has changed over time. So those records go back. I think they've actually drilled some deeper holes now, but they haven't analyzed it for climate past 850,000 years. In the southeastern part of California, we have bristlecone pines, these sort of amazing bonsai trees that live 4,000 or 5,000 years. And their tree rings are studied by people called dendrochronologists. who look at those rings, and we can tell temperature, moisture differences. And so we have pretty good records for the last 5,000 years. And recently we've discovered in the deep sea off of California, we have solitary corals that don't live with algae like a coral reef. And they actually have a stem that looks much like this. And we can now determine from the changes in the water chemistry, which are recorded in those coral, what the temperatures were like going back several thousand years. So there's a whole series of different kinds of ways we can now get paleo temperatures. And sea level, I'm not going to show you anything too much more scientific than this. So if you see a graph, sometimes you go, no, we're going back to high school physics or something. It's not so complicated. So this is just looking at the sea level history from today back 50,000 years ago, 100,000, 200, about 370,000 years. And this is the level of the ocean. We're calling today sea level, 0. But if we had been here, and this is going down 120 meters or roughly 400 feet, if we'd been here any other time, sea level would have been someplace else. And Jerry started with this, saying he was talking about the last 25,000 years, which I'll expand on, which is this period. So as the climate has gotten warmer and cooler, sea level has fallen and risen. So when we go into an ice age, we take water from the ocean that's evaporated, it falls on the continents, is ice, and sea level drops. So this is a sea level curve, but it's also a paleo temperature curve. When it gets warm like it is today, and this is coming out of the last ice age where sea level was about 400 feet lower. And I'll show you a map off here what that seafloor looked like. We melted a lot of ice. Actually, we put about 10 million cubic miles of ocean on the land as ice sheets. And sea level rose very rapidly. It went down, came back up again. And what you do see, and I'm not going to get into it because I think climate, I'm not sure what Ron and Dan talked about, but basically these are large-scale glacial cycles that are related to the distance between the Earth and the Sun. Did they talk about the Milankovitch cycles? Nope. Maybe a little bit. Wobble and the tilt. Okay. So basically the Earth is not in a nice smooth orbit, but it actually has a wobble with a cycle of about 26,000 years. It has a tilt, which gives us the season, and it's a permanent tilt, but it varies by 2.5 or so degrees, so it tilts a little further from the sun, or a little closer, and then the orbit around the sun is not a circle, but an ellipse. It has a cycle of about 100,000 years. So you can see this is about a 100,000-year cycle. But what is interesting is each of these glacial cycles, and a high sea level and a low sea level, the ice actually melts pretty quickly when it gets warm, but it falls and gets cold fairly slowly. So that tells us something about what we can expect in the future. In other words, sea level has risen pretty quickly compared to how long it took to drop. So I'm just going to blow up this last 25,000 or so years, this part of the curve. I'm going to reverse it so that now sea level is here. Going back in time 20,000 years ago. Laura, you didn't drink your water. So what we now know, at the end of the last ice age, sea level was about 400 feet lower, roughly, and it started to warm. Again, there were humans around, but they didn't have coal-fired power plants. They weren't driving cars and trucks and SUVs. So under natural conditions, the Earth started to warm, and sea level rose because ice melted, and as seawater warms, it expands. So from roughly 18,000 years ago to 8,000 years ago, and Jerry gave a great introduction on this, sea level rose almost a half an inch a year. We could actually stand out there and almost watch that. But within that roughly 10,000 year period, there were some peaks here where we think it rose very quickly, maybe an inch a year. And we now believe this is when large ice sheets in Antarctica may have collapsed and led to sea level rising fairly quickly. I mean, this isn't like quickly meaning in a year, but over several hundreds of years perhaps. And then about 8,000 years ago, it leveled off. And over the last 8,000 years, very slow rise. But this, as Jerry pointed out, did you read my paper ahead of time? No. This is pretty much the entire period of human civilization. So deltas were stable, coastal plains, fertile soil, access to water, access to the ocean. It was a time people could move from, I'll tread on archaeology and anthropology, could move from hunters and gatherers to farmers and begin to develop civilization. So human civilization never had to deal with sea level rise before. At present, that's the sea level rise rate from satellite altimetry. Right now, it's rising at roughly 13 inches per century, which doesn't sound like very much, and it's really not, but it's probably faster than it's been any time in the last several thousand years. And in fact, in all likelihood, it's probably going to accelerate. It is accelerating. And I will say something really bold, that that may be the biggest challenge that human civilization has ever had to face. So this is the shoreline off Southern California, great USGS multi-beam bathymetry map. And now they've got colors, so you can get a pretty good idea of sort of where things are. We can see Catalina Island out here. So the edge of the shelf was the shoreline 18,000 years ago. So we took 10 million cubic miles of seawater out and put it on the continents as ice sheets, and so sea level dropped. You could not get to Catalina Island, however. So that was all dry land, and then as the last ice sheet melted and that meltwater ran into the ocean, the shoreline migrated inland. At this particular location, close to where we are, maybe 10 miles over 18,000 years, or about 3 feet per year. So that gives us some sense of what might happen in the future as we get back to those kinds of rates. You can see some other things of interest here, like submarine canyons, Santa Monica Canyon, Redondo Canyon, Newport Canyon. So these were where terrestrial rivers actually crossed the shelf and cut a deep sea canyon, which is a whole nother thing to talk about. But going back in time, interestingly, one of the oldest maps I could find from, this has been redrawn, 1859, there's actually sort of a nice smooth shoreline here, way before we had LA Long Beach Harbor, and some interesting things that are now gone. Deadman's Island and Rattlesnake Island. But if you ever read a great book, 2 Years Before the Mast, Richard Henry Dana, who was here, I want to say 1820s, and what it was like, this was all mud, and they had to wade ashore in little boats, but coming to Los Angeles and San Diego and Santa Barbara in the 1820s, and what the coastline looked like was quite different before we started manipulating it. But it's interesting, another map where you can see this sort of nice, smooth, sort of a hook-shaped, half-moon bay-shaped bay, which was in its natural configuration. And we have a lot of those along the California coast. This is actually Half Moon Bay, south of San Francisco. And if you look at the coast, it's actually this sort of a perfect spiral until they built the breakwater. And basically, you get this kind of a shape. This is up at Point Reyes, the same kind of a perfect uncoiling. It's the way an abalone would uncoil. It actually has a mathematical formula. This is the northern part of Monterey Bay. There's actually two of these bays, not quite fully developed. And then this is, you may recognize, San Diego. And it actually happens when we have a very resistant headland and waves that are sort of bent or refracted around it. This is the natural shoreline shape you would end up with. But that's what San Pedro Bay used to look like. And interesting, as these maps developed, they did a lot of things. They actually built a jetty channel to get into a harbor. This was all pretty sandy and not easy to navigate. And they came out to this mysterious Deadman's Island. Maybe everybody here, that's something everybody knows about. So this is 1896. This is kind of a postcard of Deadman's Island. Apparently a lot of people were buried out there from different sailors, and there's all kinds of stories about it. And then a photograph, you can see there's Deadman's Island out there again. So it was there for a long time. This is probably right at the edge of, or within Long Beach, LA Harbor, so quite a different place. 1873, and then gradually they decided that was too much trouble to have it in the way, so they quarried it and blasted it, and pretty soon we ended up with what we see today. Very different harbor, but you can still start to see sort of some of that original shape that gave it this log spiral shape that we have today. So the coastline has changed both from sea level rising and falling, but also human activity. So as the sea level rise, the shorelines are going to migrate inland. And one of the things we notice around the world is most cities were built without any regard for sea level rise. And you might say, well, why not? Well, because it wasn't rising. And where cities were initially built was where they continue to grow. So I look at a lot of coastal hazards and storms and erosion and disaster. I love disasters. It's kind of exciting. I think most people really like disasters of one sort or another, as long as it's in somebody else's coastline or backyard. So if you look at Sunset Beach here, part of Huntington Beach, you see a lot of real estate really close to sea level. I hope it's not anybody's house, but enjoy it while you can. This is now Pacific Coast Highway, Sunset Beach, at a very high tide, December 2012, and they're waiting outside of the Best Western for something. And this is seawater, it's not rainwater. So a king tide, is that word familiar to? The real word is actually a PERIGEAN high tide, and Ron Flick may have talked about it. But essentially, not only we have these cycles between the sun and the earth, but also our distance to the moon changes a little bit throughout the year, and then, so that's gravitational attraction that gives us the tides, and then we also get close to the sun. So king tides are usually December, January, these extreme tides, and we're starting to see those having more and more impact because sea level is slowly rising, so those tides are coming even further inland. Here's another one, also Sunset Beach area, and this is getting really common in places like Miami and Fort Lauderdale and Charleston and Newport News, where they're actually sinking a bit there and sea level is rising. So we're getting an indication of what things will be like in the future already. So we've been measuring sea level rise since really the 1850s at a few tide gauges, and these were originally set up to usually around harbors and places where boats were coming in and out. We have one in Los Angeles and San Francisco and so forth. And the idea was we wanted to see how deep the water was, so as the ship's coming in out, it's not going to get caught on the bottom, so we see what the tide is before we go in and out. And we use them for lots of similar things today. So San Francisco it's the oldest in the country. I think there's one, might be Boston, that's as old. Most are quite a bit younger, but it goes back to 1850s. I think they moved the gauge here, and so we usually start with 1897. But what you can see, they didn't put them in to measure sea level, but they've been recording sea level. So you can see at the present, actually, this has just been updated. I noticed it's now 1.98 millimeters per year, or 7.7 inches. So it's gradually increasing. So you see this trend, an average trend, but then you see these pulses in here. And those are El Nino events. So when we have an El Nino, we get this warm bulge of water moving up from the equatorial waters, and that warm water actually raises sea level along the coast. In this case, in San Francisco, as much as 11 or 12 inches for 2 or 3 months at a time. So what's interesting to compare is right now the average rate in San Francisco is 7.5 inches per 100 years, but one El Nino raises it 12 inches for 2 or 3 months. So that's like more than 100 years of sea level rise. So these are these short-term extreme events that are going to be more important to our shorelines, probably at least until mid-century. And we can look at these, millimeters per year and say, well, it's really 1.98, or, that's thickness of a hair. But these events are going to be more problematic. They're acting together, though. And this is the last really big El Nino. I shouldn't say the last. One of the biggest in half a century, 1983. Many of you may remember that. And this is just 4 California tide gauge stations: San Diego, Los Angeles, San Francisco, Seattle. These are what the tide was predicted to be if you looked at the tide tables. This is what they actually were, and this is the difference. So in Seattle, it was 2.5 feet above normal because of this El Nino bulge moving up the coast. San Francisco, 1.5 feet, LA, a foot above normal. So these are things that are going to be biting at us along the way in addition to the sea level rise. So it's these short-term events. I don't know whether anybody's ever been to Capitol, this kind of cute little town next to Santa Cruz. Normally on a Sunday or Saturday, there's people out here with their lattes reading the New York Times and checking the stock market. I don't know what they do out there. But this is a very high tide in 2012. And it gives you a sense, whoa, this is supposed to be a beach with people, sunbathing out there, and I don't have a repeat. I have a repeat I didn't put in here of what this normally looks like. So these are these short-term events that are going to get us more and more often. The sort of ground zero on the West Coast has become the Embarcadero in San Francisco. Again, it was built way back when, not unlike New York, built on ship holes and fill. I mean, these are all bank buildings and financial. So this is sidewalk level, and this is high tide coming up onto the street. And this is going to get worse, but imagine another foot of high tide, or 2 feet. This picture, I don't know. I almost don't need to say anything. Solimar is up north of Ventura, kind of heading towards Santa Barbara. And I think it's something about this lady and the expression on her face, like, did somebody knock? I don't know what she's saying, What was she thinking? I didn't want my glass door to break, so I opened it up so the ocean could come in. I don't think this is Photoshopped. I don't think it is, but I just find it interesting. There's another interesting place in La Jolla called the High Tide Brunch you can have. And here's a guy having brunch. I think they have glass the thickness of Jerry's aquarium walls. So, he's having his mimosa here, whatever he's doing, and the waves he's got fish out here. And anyway, it's sort of what we're talking about at dinner. Well, if we just behave ourselves, it'll all take care of itself. I don't think so. Mission Beach in San Diego. If one was looking for a beach house, say, wow, it's got hundreds of feet of sand in front of it. It's actually got a concrete seawall here. And these are probably cheap. I don't think they're probably cheap. I'm guessing they're probably 7 figures and whatever. And this is a really nice place. But the next picture is taken from there in 1988. And we could actually find the same houses here with the brick roof if we wanted to. This one with the sloping roof is right here. So the picture's taken from right there. This is sort of like that one I just showed you from Solimar. It's like, well, you can't. It's a little light, but there's a guy coming around the corner here kind of going, whoa. And what are these people doing? Is it like Canute holding back the waves? I don't know. But here's that seawall. It's just being completely overtopped. So that 200, 300 feet of sand can disappear really quickly. So I wouldn't buy there right now. And we mentioned Balboa Island. They're really up there. They're pretty safe. So this is a low tide, but this is a high tide. So I don't know, maybe this is 8 inches or 10 inches. Not a lot of freeboard with the king tide. Belmont Shores here in... And again, I'm not trying to tell anybody to sell your house, but just as you look around, you see, we're pretty darn close. There's a couple of wonderful websites now. One's called Surging Seas, It's put out by Climate Central. Another one is a NOAA site. And what you can actually do is move the clock forward and see where the shoreline will be when sea level is higher. And this particular one, this is people know Balboa Island? It's one of those really cheap places. It's getting cheaper. So this is, and what you can do some interesting things, but this is just current water level, and you can go up 1 foot at a time. There's also, interestingly, another inset here where you can say, look at property value, like millions of dollars per acre, population per square mile, social vulnerability, which I didn't do. So we're starting out, this is today, like high tide. So we added 1 foot. And if we go back, you can see sort of what's happening to these streets over here. 1 foot above present high tide. There's 2 feet. Balboa is becoming Venice. And I think I went to 3 feet. It's all underwater. And that's 3 feet, which that's sort of an average number for 2100. Many people think it might be much higher. So, 2050, 1 foot sort of the average minimum. So anyway, this is giving you some sense of what's going to happen. And Newport Beach, interestingly, Balboa has this little seawall that keeps getting overtop. So they just decide to spend up to $2 million to build a 9-inch high wall on the top of it. That's called aggressive incrementalism. What? I was not a consultant on that. No. But I mean, it's interesting. Let's do a little bit at a time and so forth. I don't think it's going to last for too long. And now we're getting closer to home, Jerry. It's a little different because we've got a lot of walls and bulkheads and so forth. But so the aquarium's right here, I think, right? Yeah. So this is today's sea level, say high tide. It doesn't look quite as dramatic unless you just watch it change. This, we'll just add 1 foot. See any differences? A few places. And then I did 2 feet. I think I stopped there. Oh no, I went to 3 feet. So anyway, you can do this in your front yard or San Francisco or whoever you want around the U.S. coast that you want to antagonize. Yeah. So you can, it's like a Google Earth map. You can just zoom the scale and just move it along and then hit all the way up to 10 feet, which 10 feet, well, I don't know whether Dan talked about the possibility from the sea level rise study in California. I mean, that's an extreme by 2100. Not impossible, but pretty extreme. This is something I wrote a couple of years ago, and people were saying, well, we're not going to move back. We're going to hold our ground. Well, it turns out we've been losing land for a long time. This is, you may have seen pictures of Pacifica, south of San Francisco, and these were a series of apartment buildings. They kind of get bought and sold like, I don't know, stock market. This is actually not rock. We could call it something really fancy like Quaternary alluvium, but it's basically dirt. And what has happened these were built in around 1970s. There was some land in front of them, but not a lot. Why they built, I don't know, it was pre-coastal commission. And what's happened basically is this has continued to erode. These two, this is sort of a temporary, not really going to last very long. They actually, contractor said, we're going to save them, and they hung people over the side of the cliff with a drill rig and drilled back in what they call soil nails or tiebacks and gun out of the cliff, and it all failed, and now they're gone. So this is happening. It's not new, but most people don't really want to think about it. This is a place on the Sonoma coast. It's called Gleason Beach. Some people call it Malibu North. But there's a whole series of houses. I think there's 21 houses built. And this is Highway 1. I don't know quite why they sold the lots on this side. All their septic tanks are on the beach behind some seawalls. But this is a really, it's a type of rock that is common along the coast called the Franciscan Formation. It has some really resistant blocks in it, and then everything else is very sheared up sandstone and shale. It's actually seafloor stuff that was sort of plowed up and scraped off onto the coast. And if you look at it now, most of those houses are gone. In fact, if you stand out and look at the roads are right there, the walls are gone, the septics are gone, most of the houses are gone. The other ones are probably pretty inexpensive, I would guess, right now. And then closer to home, one of the things we see from place to place are not just small rock falls or particle by particle failure, but huge, massive landslides. In Portuguese Bend, we've known about for decades. I want to say back in the 50s. And there's some unique geological conditions. There happens to be a layer of expansive clay and road runoff and septic tanks. So the original back of the slide is way back here someplace, but you can see all these individual scarps, and you can actually see the fresh asphalt here where if you drive through it. It's kind of exciting. It's like a roller coaster. But I think people are still living on it. I think they're just moving with it. And then we even have very close Sunken City, which is another landslide. Just up the coast here, and you can see where the road used to be. So this is another way that large chunks of land fail in somewhat unique settings where the geology is such that land is very unstable. In fact, I didn't realize this has become sort of an art gallery of sorts. I don't know. There's quite a few pictures online if you look at Sunken City. And I'm just spreading this out so nobody feels like I'm picking on them. I'm sure many of you know Isla Vista. Maybe some of you live there. I did. And this is, do people know about the California Coastal Records Project? So it's this wonderful, pardon me? Yeah. So it's a couple that I work with that live in Santa Cruz, and they actually started photographing in 2002 in a helicopter the entire coast from Crescent City to Imperial Beach. I had old colored slides, actually from Boating and Waterways, from 1972 and 1979, and so I told them, I said, oh, great, we'll scan them. So we scanned 13,000 slides and put them on there. They are from old colored slides, though, so they're not high-resolution digital photographs like we would have today. But still, this is Isla Vista, 1979, and you can get some idea. The cliffs here are not stable, so there's 5 units here, and there's 4 more here, and you can see they've got decks and so forth. So the next picture, so I'm blow up that area sort of. This is now 2013, so all those decks are gone. Most of this is gone, and these have all been removed. So, pardon? Go back? So, and these are all online. You can, it's open access. They have now flown it in 2002, 2004, 2005, 2007, 2009, 12. 2015 or 13 was the last one. And these are 35 megabyte images, so you could blow them up, and they're quite spectacular, every inch of the coastline. Anyway, so big changes. Within, relatively few years. I was going to mention this. People know Broad Beach? So this is Malibu North or Malibu West. It's funny, when I grew up out in the San Fernando Valley, and my dad was a high school teacher, and they never had any money, but he said, I bet someday this place is going to be valuable. This was about 1953. My dad also thought Southern California was too crowded in 1950, so we left and moved to Oregon in 1950, and if he would have only known what was happening. Anyway, they came out to what this is called actually Trancas Beach before it became Broad Beach, and they actually bought a lot up here for $2,500. He borrowed money from an uncle, and they were so happy they sold it for $5,000. They bought 2 lots, actually. So this is what Broad Beach looked like in 1972. Pretty much, I would say, little beach cottages, pretty much. I mean, some of these are really small. So we're going to fast forward to 2013, and you'll see this same little stream channel here so you get an idea of where we are. So this is now 2013. So some people bought two lots or 3 lots, and what's interesting is this broad beach is gone, and it's pretty much disappeared. They put their septics out here on the beach. There's no sewage system, so their septics are in front of their houses, which you don't want those to be uncovered. And they've gone through a long trial with the Coastal Commission and so forth. It turns out their beach is gone. It went from broad beach to not very much beach at all. And there's reasons why. I'll come back to this house in a second. But essentially, they went from sandbags, because the Coastal Commission didn't want them to have their septic exposed, but also didn't want a permanent rock wall, a revetment. So they let them do this, which lasted for about, not even made it through the first winter. And then they got rocks, and now they're trying to find sand to put on the beach, which they're having a hard time doing. So one of the people that lives there, you may recognize. He's the one on the left. The famous one. He's the famous one. So anyway, Pierce Brosnan is one of the people that lives there, and it's a pretty exclusive neighborhood, but they've got a problem, and there's no easy solution in sight. So another issue is the weather going to be changing in addition to sea level rising? More storms, or El Nino's going to be sort of the regular event? And still a little bit of question about, are the waves getting bigger? Are they getting bigger faster? There's some tendency to see that in addition to sea level rise. The other thing that we've now begun to recognize, how are we doing on time, Jerry? Okay, we're doing fine. Does the word PDO mean anything? Okay, so Pacific Decadal Oscillation. We tend to think about El Nino or ENSO, El Nino Southern Oscillation, and those are individual events that last a year or so, but those events are part of a bigger sort of set of climate intervals, and these are actually going back to roughly 1900 to 2015-16, and these are basically surface temperature anomalies in the Pacific, the North Pacific. And as the water gets warmer and cooler, that affects a lot of other things. The warmer it gets, the more evaporation tends to affect surface air temperature and wind patterns and storm directions, and more evaporated water means more rainfall and more mud flows and more floods. And it turns out there are cool, or what we call negative, Pacific decadal oscillation cycles, and positive, which are warmer. And without me trying to convince you of that, there seem to be some patterns in there, right? You sort of squint your eyes a little bit, you see some red patches, and some blue patches, and some red patches, and some blue patches. It's not perfect, but there's definitely some things going on here. In fact, if we broke it up, it turns out from maybe the 20s to about 1945 was a warm, more El Ninos, because these events are El Nino events, more storms, more coastal erosion, more rainfall, more flooding. Interestingly, this all corresponds also to changes in marine life, and this is the peak of Cannery Row. The sardine fishery was part of a warm PDO cycle. In about 1945, late 40s, it just collapsed. And people thought, well, we overfished. It's a factor. We introduced DDT in the Salinas Valley about the same time. But it's also part of a long-term climate cycle. And it turns out it switched to a cool, calmer, fewer El Ninos, more La Niñas, less severe storms. And actually, anchovy tend to replace sardines, which feed on a different kind of plankton. 78, Cannery Row was gone, and we had all the stuff on Cannery Row today. Hotels and restaurants and Bubba Gump shrimp and all the other stuff there. Probably 17 Starbucks. And 78, it switched, and it came back into an El Nino-dominated cycle again. We had the big El Nino of 78 and 82, 83, and 97, 98. But interestingly, this is the period of California's coastal development. So after World War II, people flocked to California. And if we put a population plot on here, it really skyrocketed in the 50s and the 60s. People developed the bluffs, the beaches, the cliffs, because the temperature was great and the land looked stable. It's sort of like we gave away all the Colorado River water when we had a lot of water, and now climate changes, there isn't enough water. So we sort of set ourselves up without knowing it for disaster. And when this El Nino hit, or these series of El Ninos, whoa, what happened? A lot of damage. It switched back again in the late 1990s to it, and actually the sardines came back. Only nobody ate sardines anymore. Actually, sardines does anybody know, this is a good question for you guys, you're all educators and really smart people. What's California's biggest fishery year after year after year? What? You didn't hear him, did you? Huh? No, it is squid, yeah, but I mean, most of us don't think about that. You know, you calamari on the menu, maybe every year you'll have a piece of it or something. But almost 2/3 of our fishery and tonnage is squid. And where's it go? It goes overseas. Sardines is often in the top 4 or 5. That all goes overseas. Urchins. What do you eat? What do you eat an urchin for? Well, yeah, you kind of take the sexy organs inside and you put them on sushi and stuff. That all gets exported. The few things that are valuable here, we keep our Dungeness crab. I'll ask my class, what's California's biggest fishery? And they'll say, abalone? Abalone is like, eating a dinosaur. There's just not too many around. So anyway, this reflects our fishing as well. And sardines came back here. We went into a cool cycle, and now we're back in a stormier cycle again. But in generally, these will last 20 or 30 years. So this doesn't bode well for the immediate future. And it's really hard to balance this with, 5 or 6 years of drought, and how does that fit in? And climate is changing. So warm El Nino, cool La Nina. Jerry talked about mitigation and adaptation. And I did a book about 6 months ago called Coasts in Crisis, A Global Challenge. And because most of my work had been on the California coast, I said, I've got to get abroad. I mean, I've been fortunate to travel a lot, but my wife and I spent a month driving around the coast of England and Scotland. We drove, and then we spent a month driving around the coast of Spain and Portugal. We drove 5,000 miles. I wouldn't recommend doing it, but it'd be nice to spend a little bit of time in one place, but we had the 2 plane tickets, and so. But anyway, I found this book because I think about coast and coastal erosion. I showed you Gleason Beach and so forth and so on. The Lost Towns, the Yorkshire Coast, and other chapters bearing upon the geography of the district, and written 106 years ago. And it turns out, if you've ever been on the Yorkshire coast of England, it's all glacial deposits, and it's pretty much weak clay. It's like mush. And what this book writes about and records is all of these towns, 31 towns have been completely lost over the last 2,000 years. The British keep track of stuff. The Romans were here. And it's interesting, just the names of these towns, Old Witheransea and Old Newton and San Lemaire and Ronkwickle. And anyway, these red dots aren't there anymore. They're towns that were lost. And I thought, well, I got to see this place. How are they dealing with it today? Well, it turns out there's lots of roads that just disappear. They go, do not proceed. And welcome to Clifftop Caravan Park. So what they've done is something really interesting. It was very rainy. You can see these little drops on the... their mobile homes or trailers are called caravans. And this is sort of what it looks like on the ocean side. These huge erosion scallops. And this has been going back on an average of 6 feet per year. So they've done something very creative. And you can go on Google Earth and do this. These are caravans or trailers, and you can see these roads that go out that disappear, and you can see all these empty concrete slabs. So instead of building multi-million-dollar homes that then you've got to build seawalls to protect and so forth and so on, and a few people who can afford it get that ocean view. These are sort of average people who can buy a mobile home. We went in to ask what they cost. Oh, how much you want to pay and how big do you want? I mean, from $10,000 to $50,000. And you get to park it here someplace. And these are kind of interesting. Gosh, they have pubs and casinos and swimming pools. They even have old people racing in wheelchairs. I mean, it's all kinds of really cool stuff. But when you get to the edge, you just pick it up and move it, and you start at the back like, dominoes or something, you start all over again. But there's no big infrastructure. There's no big cost. You just hook a trailer or a truck and move it back again. And there's dozens of these along the Yorkshire coast. And I thought, it's not what I'd recommend, but it's very resilient. We're always looking for resilience. It's very sustainable. You just keep moving. And mostly these were sheep pastures and cow pastures, so it wasn't like Balboa Island or, Newport. So kind of looking again at another coast, and it's easy to pick on the East Coast. These are the 25 cities most vulnerable, according to FEMA, 100-year coastal flooding. And what's interesting, is there anything distinct about this list? And these are the numbers of people in thousands that are at risk today. Well, you pick it out. They're all in Florida except for these three. New York's the big one, Charleston and Atlantic City. And then we can go forward to 2050. And we added a couple more. We added Virginia Beach and Boston. But the rest of them are all still in Florida. And Florida is building like there's no tomorrow. And there's no sea level rise. Florida has what are called nuisance flooding. And you may have read a little while ago, Florida, North Carolina, Virginia, they wouldn't let them use sea level rise. They used coastal flooding. North Carolina sort of outlawed sea level rise, which was an interesting approach that was on the Colbert Show. He said, they figured it out. They just outlawed it. For any future development, you can't, or controls, you can't use the sea level rate any higher than what it's been in the past. Which is like saying, the weather can't get any worse than it was last week. So Miami's got a problem. New Orleans is all below sea level. These are really big problems because they're already below sea level. New Jersey, New York from Sandy. So I don't know whether Dan Cahan showed this image. We were on a National Academy Sea Level Rise Committee for California, Oregon, Washington. We're asked to look at the past, present, and future. And so this is an extension of that, one of those earlier plots. So this is sort of geological evidence from 1800 to roughly 1900. Pretty flat as far as we can tell. We began with tide gauges here, but if we look at the record of tide gauges up till late 1990s, the best we can tell today, it averaged about 1.4 millimeters per year. That's about 4 or 5 inches per century. The challenge with tide gauges is we have one at Long Beach or Los Angeles, and we have one in San Diego and La Jolla and Santa Monica and San Francisco. They're anchored on land. It's a water level recorder. So we put this on something, a pier, a wharf, a breakwater, and then we're measuring what water is doing relative to that tide gauge. But if the land is rising or the land is sinking, it's going to record that relative difference. So if you live in Alaska or parts of Scandinavia, British Columbia, the land was depressed by thousands of feet of ice, sort of like sitting on your mattress, and the ice melted, the land is rebounding, but it takes thousands of years. It doesn't respond as quickly as your mattress. So in Alaska, Juneau, the land's doing this, and sea level's rising, but it's rising slower, so relative to the land, sea level's actually getting lower. New Orleans, Venice, Miami, the land is sinking. So here's sea level, same sea level, global. The land is actually sinking. So sea level is rising faster. So when we got these global numbers, this is an average. And the question is, were all those tide gauges evenly distributed about the entire planet? Well, most of them in North America and Europe, so we forgot a lot of the rest of the world. As time has gone on, we've refined this, and it keeps dropping. But in 1993, some really brilliant people said, so we call these local or relative. Let's measure it from space. And so we launched a couple of satellites that have been replaced, and they were actually using radar, sending down zillions of radar beams to the ocean surface. Can you think about the ocean surface? How do you measure? Ocean's going all over the place. How do you measure down to 1/10 of a millimeter from 200 miles or 100 miles up? Well, you have to know exactly where those satellites are down to 1/10 of a millimeter. But that's what people do that are really smart. We call them geodesists, and military people who want to know where everything on the planet is relative to satellites. So we launched those in 1993. They've now been up for 25 years. And they're showing a rate 2.5 times as high. So it's going up. And part of our study for California, Oregon, and Washington was the future. How do we know where it's going to be? And they wanted to know 2030. This was when Arnold Schwarzenegger was governor of Oregon, Washington. How about 2050? How about 2100? How do we know that? So I'm going to ask you a comparable question for the young people in the audience. I'm going to ask you today, you're going to, I don't want to be too prejudicial. Someday you might have a family, and you might have children, and you want to send them to college. So let's say that's 20 years from now or 30 years from now. What's it going to cost to go to college 30 years from now? I mean, we don't even know what's going to be next year. Is it going to cost, today it might be, if you're in a community college versus Stanford or Harvard or University of California, it's going to be $10,000 or 20 or 30 or 40, 50 or 60, or NYU might be $70,000 a year. But in 30 years, is it going to be $500,000 or $1 million? I don't know. Or how about if you want to retire? You haven't even graduated. You're going to retire in 50 years. Some of us never retire. Jerry's never. We promised each other we'd never retire, right? What's it going to cost to retire? How much money do you need in your bank account? And some of you are my age. You say, well, we've got it all covered. We're okay. But then the tax structure changed, so we don't know what we have anymore. But it's hard to project 40 years into the future, 30 years into the future. So it's like that with climate, because there's things that are scientific and things that are political. Because a lot of this future depends on carbon emissions. Carbon dioxide, burning of fossil fuels, making cement, burning vegetation is a big factor. So we did a couple things. One is using empirical, sort of using past climate. So we know 130,000 years ago, sea level might have been 10 or 20 feet higher, and temperatures were about what they are today. 3 million years ago in the Pliocene, sea level was 30 feet higher, and temperatures were not too much different from today. So those are sort of empirical relationships. And then we have models. Everything today is modeled. I'm not a modeler. I observe stuff. I like to go out and watch it and measure it. And I'm always bugging these people. Well, how do you know? And there's 50,000 models, and everybody uses different parameters and weighs things. And I talked to a friend. He says, Gary, models are models. They're all wrong. But maybe they tell us something about the relationships between different things. So if we know what carbon dioxide will be, we can put that in along with cloud cover and all these other things. So a big range. By 2100, it might be 16 inches. It might be 4.5 feet. And planning for that's difficult. But you can see it starts to diverge pretty quickly. And we could call this, uncertainty. And in the words of one of my favorite climatologists, there are the known knowns, there's the known unknowns, and there's the unknown unknowns. I need to put a picture of Donald Rumsfeld up here so you know where that came from. But when I show my students that, they don't know who Donald Rumsfeld is, so it's not funny anymore. And then this just came out from the National Climate Assessment just in the last couple of months. So the nation does a study much like the IPCC, the Intergovernmental Panel on Climate Change, does, and part of that is sea level. So this is sort of where we are today. So this is the long period of, much like the one I just showed you, this is geologic record tide gauges, satellites. But from there, where do you want to take it? And as Jerry said, we baked in a lot of carbon dioxide. So most people are thinking, I don't think we're going to make this low one. And the questions are now, what's the trajectory? And for 2 years, carbon dioxide globally leveled off, and now it's up again. So we're not really doing much yet. And God bless you drove a Prius tonight, and you changed all your light bulbs, and you turned the water off after you took your shower and brushed your teeth, but that's not going to do it. We've got to do a little more than that. So, but you can see nationwide somewhere between, I don't think, we're already faster than this now. We're 13 inches per year. So 4 feet, 3 feet, 8, I mean, these are all possible. And here's where the big uncertainties are. So I don't know whether Ron and Dan talked about this, but if we took all of the mountain glaciers on the planet, the Alps, the Andes, Patagonia, Alaska, the Himalayas, if we melted all of that, how much could sea level rise? Quiet. He knew what he knew. Pretty good. It's maybe 1.5 feet, 2 feet, in that range. So they're actually quite small. How about Greenland? You can see I'm kind of leading you along the path. If we melt all of Greenland, 6 feet? 6 feet. Do I hear 8? 10. Do I hear 20? How much? 10 meters. Pretty good. We usually say 7 meters, so 7 or 8. 24 feet. Are we okay here? I don't think so. No. Okay, what's left? Antarctica. The 800-pound iceberg. About 190 feet. So together we have about 215, 16 feet of sea level built in if we melted all the ice. And that's happened in the geologic past. We have had periods when all the ice is melted, and we've had a period called snowball Earth when we think everything was frozen without humans around. But the challenge is, during all those periods in the past, there weren't people here. And there's people that are sort of, I won't go into the whole issue of climate change and all. Say, well, sea level's been much higher and lower 100 million years ago. Well, it has been, but there weren't any people here. There weren't any cities. We didn't have an agriculture base and people dependent on water and all kinds of other things. So these are huge, but the point is, this isn't going to happen tomorrow, this year, this century, next century. I won't venture too far beyond that, but we don't need it all to melt. All we need is, as I showed you in Balboa, is 1 foot. Or 2 feet. So there's a lot of potential there. Oh, the video. We're ready. Has anybody seen Chasing Ice? Okay, this is just 3 minutes. It's not the whole 2 hours. So these guys are graduate students on Greenland documenting the end of this glacier, and I think they're getting a little bored, and they're freezing their rear ends off, and they're calling back to their professor saying, well, everything's kind of going along, and then all of a sudden, it all breaks loose. We got our guy up there. Okay. I think it's about 3 minutes, maybe.
I'm on the phone with Jim on one of our regular check-ins. Jim, nothing's happening.
Nothing's happening.
Jim, it's going well. We had some serious bouts of wind.
They're on rock,
but
by
other
the way.
than
They're
that,
not on ice.
things are fairly well set up here. We've got some continuous time lapse going.
It's starting, Adam, I think. Adam, it's starting.
Oh, wait, Jim,
I'll call you back.
the big piece is starting to cast. Let me call you back.
Call him back.
Call him back.
Okay, bye.
Still going?
Yeah, in that V section right there. Holy shit, look at that big bird
He
rolling.
said, holy.
All four are running, right?
They've never seen anything. All the
Look
time
at
they've
that.
been up there. Nothing's happened.
You see how, look at the whole thing.
calving faces 300, sometimes 400 feet tall. Pieces of ice were shooting up out of the ocean 600 feet and then falling. The only way that you can really try to put it into scale with human reference is if you imagine Manhattan. And all of a sudden, all of those buildings just start to rumble and quake and peel off and just fall over and roll around. This whole massive city just breaking apart in front of your eyes. We're just observers, these two little dots on the side of the mountain. And we watched and recorded the largest witness calving event ever caught on tape.
So how big was this calving event that we just looked at? We'll resort to some illustrations again to give you a sense of scale. It's as if the entire lower tip of Manhattan broke off, except that the thickness, the height of it, is equivalent to buildings that are 2.5 or 3 times higher than they are. That's a magical, miraculous, horrible, scary thing. I don't know that anybody's really seen the miracle and horror of that. It took 100 years for it to retreat 8 miles from 1900 to 2000. From 2000 to 2010, it retreated 9 miles. So in 10 years, it retreated more than it had in the previous 100.
You can actually buy this. I didn't buy it, I just took it off the web, but they have these for other places. But this is melting all the ice, which I said it's not going to happen anytime soon. But it's interesting because this is, you know, Isla Palos Verdes, and kind of interesting Dominguez Mound. And this goes clear back up to, you know, Whittier Narrows and X-Lax. So you can see what it would have looked like with a lot more sea level. So this, I mean, I'm not trying to scare you. It's another view of way off in the future when none of us will be here. So the future, what are our options? Jerry mentioned we have 3 options: mitigation, adaptation, and suffering. We're already doing some of each. The only question is what the mix will be. The more mitigation that we cut back greenhouse gases, the less adaptation and suffering will be required. So there's a couple approaches. We can ignore it or call on some higher power. We can accommodate it somehow. We can build barriers, seawalls or dikes, or we can relocate, or what we've been calling managed retreat. Well, there's denial, not rising. And, you know, there's an old story of King Canute, who they were flattering him, saying, you know, you can stop the sea. And he said, well, put my throne out in the water. I'm going to try to stop it. And he kind of got so mad at him, he finally threw his crown on the ground and said, I'm just a normal person, but you guys can't give me that power. I can't change the water. And we can, you know, build an ark. Accommodation, you know, we can build houseboats and floating cities. There's a few places we can do that, but right now we've got maybe 200 million people living within 3 feet of high tide. I don't think we can put them all on boats. So these kind of dreamy future scenarios like this. Who, you know, look at these boats. Who gets to live here? You know, it's not going to be Bangladesh and Dhaka and so forth. And then we could do Dubai, but there's another difference. When we haven't sort of built land out and their economy is sort of crumbling now, but I don't think that's the way we're going to accommodate the people. Engineering approach. There's a place where we built these massive floodgates. The Thames in London has these things they bring down at high tide, Rotterdam, and then Venice has got this giant system to keep the water out. This is a giant corrupt process that, if you read about it, I think it's up to $5 or $7 billion, and it's just a few more feet. It's like the wall at Newport. And then the hard approach. We can build more walls. Coastal Commission is not excited about approving any more walls. This has been called the Great Wall in Encinitas. We got this in Malibu. This is one we built in Santa Cruz that actually looks a little more like rock. It's still a wall, and it has a lifetime. Or we can relocate things. Cape Hatteras Light, we can move big houses, but there's a lot of places where we call this unplanned retreat. Wicked is being used now for a problem that doesn't really have a solution. Not that it's nasty, but so Miami, they're building between Miami and West Palm Beach, there's 50,000 condominiums being built with no regard for sea level, and they're sitting on Swiss cheese or limestone. Gold Coast, I just threw in Coronado, or Long Beach, a lot of people very close to sea level. So I promised my 2 granddaughters I would do everything I could do, but we have exactly enough time if we start now. And I'm going to leave you with 5 2-word messages. It's real, it's bad, it's us, scientists agree, and there's hope. But I'm going to add one more, in California. Thank you.